Good evening everyone. I am very happy to invite you all to this meeting of the Calculus Forum. In the last two meetings we had discussed on topics related to sequences and series. This is the third meeting in this semester and we shall focus on continuity related problems and their solutions. 2 weeks back Kuntal and myself had gone to a quiz competition and one of the rounds was purely based on calculus and we would like to share some of those questions with all of you today. So, we have amidst us Professor Ranganathan, Professor Arindama Singh, Professor Tamban Nair and Professor Kulkarni. We sincerely thank you for sparing your time. So, let us start the discussion. Kuntal, would you like to initiate?
Please display the first question. Yeah, thank you. So, the first question is like this. F is a real valued function defined on the closed interval minus 10 to 10. And it is given that it is continuous on the whole closed interval minus 10 to 10 and it is differentiable in the open interval minus 10 to 10 with the additional condition that f dash x is bounded above by 2. Now if f of minus 10 is minus 20 and f of 10 is 20, we have to find f of pi plus e. So we are given 5 minutes time and we are able to solve this. So anybody will give try?
From the problem, you can see that if you take the function f of x equals to 2x, okay, then this function also satisfies all the property like f dash x less or equal to 2 and f of minus 10 is minus 20 and f of 10 is 20. Therefore, from here we can say that f of 5 plus e equals to 25 plus e. Am I right?
Yeah, that's right. So that means there is a function, right?
Yes.
So is it the only function having this property is a question?
Yeah, means you want, is this the only unique function?
Yes,
you want,
right.
So existence is given by Mansur. So I want to give some hint. For showing the uniqueness of the given function, of the given problem, whatever the property satisfies the given problem, I am taking gx equal to fx minus 2x for all x belongs to minus 10 to 10 close interval. Then we can clearly see that g is a differentiable function in the open interval minus 10 to 10. Also, you can see that after taking the differentiation of g dash x is nothing but f dash x minus 2 for all x belongs to minus 10 to 10 open interval. Okay. That means we can see that g dash x is less than or equal to 0 for all x belongs to minus 10 to 10 open interval. Because we have given f dash x less than or equal to 2 for minus 10 to 10 open interval. That means we are getting that g is a decreasing function in the open interval minus 10 to 10.
Yes.
So Kuntal, am I in a right track?
Yeah, go ahead and complete the solution.
Yeah, given that, so we have f of minus 10 is equals to minus 20 and f of 10 is equals to 20.
Yes.
Therefore, g of minus 10 which is equals to f of minus 10 minus 2 times minus 10 which is equals to 0 and g of 10 is equals to f of 10 minus 2 times 10 which is equals to 0. And we already established that g is a decreasing function and g has two zeros at the end points minus 10 and 10. Therefore, g has to be identically 0. Therefore, fx is equals to 2x. So, here thus we have seen that fx equals to 2x is the only function satisfying the given properties.
This was a nice problem to start with. And you are asked to find some value of the function at some point. You see that the properties what the function is required to satisfy is really consistent by showing that there is one function which satisfies all these properties, namely f of x equal to 2x. Now, next you see that to get that value at certain points, you have just evaluated this function f of x equal to 2x at that point, and that satisfies one of the values. But then there can be other values. So you ask the question whether there exists a unique function satisfying all these properties, and you could prove that yes, it is the only function that is possible.
Yes.
So the question could have been something like find the value of. However, that gives a hint that there is a unique function. So it was hidden in the problem, and you could have discovered it. That's good.
Yes.
In the quiz, I don't think we thought so much. We just assumed that it should be 2x, and since it was satisfying all the properties, and then we gave the answer and we got points also. So we got to know something more here. There was another problem in which we couldn't score points. So that was a pure algebra problem. We couldn't use any calculus hint to solve that problem. So the question is displayed here. Let A, B, C be positive numbers such that the product ABC is equal to 1. Prove that A squared plus B squared plus C squared is less than or equal to A cube plus B cube plus C cube.
If A is strictly greater than 1 and B is also strictly greater than 1, also if C is strictly greater than 1, you can see that the problem is trivially true, because if A is strictly, B and C all are strictly greater than 1, then A square plus B square
but
plus
this
C
cannot happen, the product is 1.
No, without using that condition we can solve the problem.
No, but this is a problem with the constraint.
Yeah.
Sure.
No, that I am just saying.
just
After that I am
Oh.
coming to the problem. If means without using the condition product of ABC equal to 1, the inequality is trivially true. Means we can solve the problem. But suppose we want to use condition product of ABC equal to 1, then I think we can solve that problem using AMGM inequality. See, here ABC are positive real numbers, it is given. Okay, that means we can solve using arithmetic mean and geometric mean to solve this problem. That I am guessing actually. Okay, also we note that for all rational number p by q, a raised to p by q, b raised to p by q and c raised to p by q, this product of all these things also 1, because ABC equal to 1 we have given. And from here also we can see that geometric mean of a raised to p by q, b raised to p by q and c raised to p by q also equal to 1, correct? But given problem is we are asked to prove that a square plus b square plus c square less than equal to a cube plus b cube plus c cube. So to solve this problem, how to connect with a square plus b square plus c square with a cube plus b cube plus c cube, that I am not getting.
See, your observation you have made are all very good observations. If you look at root A, root B and root C, they are all positive. And not only that, their product root A, B, C is again 1. So if the problem were to be true, then we should have root A square, that is A plus B plus C should be less than or equal to A power 3 by 2 plus B power 3 by 2 plus C power 3 by 2. And for the same reasons, you see, I could have taken A power k, B power k, C power k for any natural number n. Then also we see that they are all positive and that product is 1 again. So if the problem is correct, then we must have A power 2k plus B power 2k plus C power 2k has to be less than or equal to A power 3k plus B power 3k plus C power 3k.
Sir, in fact, a to the power 2k plus b to the power 2k plus c to the power 2k less equals to a to the power 3k plus b to the power 3k plus c to the power 3k for all rational number k.
Yeah, so you're right. We can go a step ahead. Now, for any real number x, see, this again says that a to the power 2x plus b to the power 2x plus c to the power 2x is less than or equal to a power 3x plus b power 3x plus c power 3x. Now, what does it suggest?
Yes, sir, it looks a power x plus b power x plus c power x is an increasing function of x.
So let you try the. So take the function f of t equals a power t plus b power t plus c power t with abc equals 1, and then prove that this function is an increasing function.
Let me try this, sir. So I am going to compute the derivative of f at t. So f dash at t is equals to a power t log a plus b power t log b plus c power t log c. Now we have to show that f dash t is bigger than or equals to 0 to show that f is an increasing function.
Hassan, there is some problem. You can see that your f dash t is equal to a raised to t into log a plus b raised to t into log b plus c raised to t into log c, correct? Yeah. So here a raised to t, b raised to t, c raised to t all are positive. We have no problem. But we do not know whether log a, log b, log c are positive. Even we do not know whether these are log a, log b, log c, these are non-negative. So we cannot say that a raised to t log a plus b raised to t into log b plus c raised to t into log c, this is greater than or equal to 0.
But we have another given condition, which is the product of ABC is equals to 1. So we can use that one to compute the value of f dash 0 is equals to log A plus log B plus log C, which is equal to log of ABC, which is equal to log 1, which is 0. Therefore, we get f dash 0 is equals to 0.
This is correct, Tapas. If log A, log B and log C are squares of real numbers, and in that case a power t log A plus b power t log B plus c power t log C is certainly non-negative.
Yes, Santi. For example, you can take a raised to t into log a whole square plus b raised to t into b whole square plus c raised to t into log c whole square, and that is greater than or equal to 0.
Yes, yes, of course.
But Santi, look at the last expression. That is nothing but the second derivative of f at t, and this is bigger than or equals to 0. Therefore, we have that f first derivative of f is an increasing function on R.
Yeah. So you have proved now that f prime is an increasing function. Is that right? What else do we know about f prime t?
Okay, we have that f dash at 0 is equals to 0, and we have proved that f dash is an increasing function. Therefore, f dash at t is bigger than or equals to f dash at 0, which is equals to 0 for t bigger than or equals to 0. So this shows that f is an increasing function for non-negative values of t.
Now I got it, because you can take for 2 less than 3 f of 2 less than equal to f of 3, because it is monotonically increasing function for t positive, for all t positive. So f of 2 less than equal to f of 3. Okay, from here you can see that f of 2 is nothing but your a square plus b square plus c square, and f of 3 is nothing but your a cube plus b cube plus c cube. So that is why a square plus b square plus c square is less than or equal to a cube plus b cube plus c cube. Now our problem is over.
Excellent. Actually, we have proved a much general theorem, like if a1, a2, etc. an are all positive numbers such that their product is 1, then for any two positive numbers x less than y, we must have a1 to the x plus a2 to the x, etc. plus an to the x is less than or equal to a1 to the y plus a2 to the y plus etc. an to the y. So we have actually proved a much general theorem. So you see now that how a good problem solver's mind works. Right?
Yeah, it's really unfortunate that we couldn't solve this problem there. But actually we can excuse ourselves. Within the given 5 minutes, I don't think we would have thought so much.
Well, probably you can try another simpler problem. Susmita, can you please display it? Maybe you can try it. It's given that f is a continuous function on the interval ab, closed interval ab, and it's differentiable in the open interval a comma b. If f dash x is not equal to 0 for any x in ab, then show that f is 1 to 1 in ab. Can you try it?
I want to use the mean value theorem and use this thing by contradiction method. Okay. So suppose f of x1 equals to f of x2, where for some x1, x2 belongs to open interval a comma b and x1 less than x2. Okay. Then by mean value theorem, f of x1 minus f of x2 by x1 minus x2 equals to f dash c for some c belongs to open interval x1 comma x2, right? Since f of x1 equals to f of x2, therefore f dash c equals to 0, and which is a contradiction because we have given that f dash x not equals to 0 for all x belongs to open interval a comma b, and therefore we can conclude that f is one function.
That's good. So this is an application of mean value theorem. That's, you have rightly pointed it out. So can you tell me some question which you have got in your quizzes about mean value theorem?
So, see, another point is that what is given is f dash x not equal to 0, then you showed it's 1 to 1. Suppose you want to show that this is increasing or decreasing. Is it possible? That is f dash x non-zero means either it is strictly increasing or it is strictly decreasing. It is possible because we can use the so-called intermediate value theorem, right? Strictly increasing means what? That is f dash x has to be either strictly positive or strictly negative. What is given is only non-zero, right? That means once it is non-zero, it has to be either strictly positive for all x and or strictly negative for all x. So this will follow from the so-called intermediate value theorem, right? Another point is that once it is differentiable, this f dash always have intermediate value property. You don't have to even assume f dash is continuous. So that is also getting, not only that is 1 to 1, it is like this. So, all right.
So another interesting fact is, suppose you draw the graph y equal to f of x, right? And then look at the possible slopes in the interval a to b, and then look at the possible slopes fx2 minus fx1 by x2 minus x1. Now this set of slopes is actually an interval. The set of slopes is actually an interval. That is, if you have two cards with slopes, say c1 and c2, and some d is in between, then you have a slope which takes that value, slope of value d. So the slopes, actually the values that the slopes take, that itself is an interval.
That's why they can use intermediate value property.
Yeah.
That was a good discussion. Now, do you have any questions in your quizzes where you want to use mean value theorem?
So you can take this question like this. So now you have a continuous function on the whole real line R, and it is differentiable also with the given condition, extra condition like the first question, f dash x is bounded above by 2. So in the first question we are giving only the value at the two boundary points minus 10 and 10, but in this case it is only given that f of 2000 is minus 4. So you have to find out the maximum possible value of f at 2018.
Any suggestion as to how to go about?
Yeah, if we summarize Kuntal's problem, Actually, we have given value of a function at certain point, and also we have given that derivative of the function is bounded above throughout whole real line. And we are asked to find the value of the function at another point.
We can use the solution of our previous problem and show that fx minus 2x is a decreasing function.
Now I am going to approach the problem in a totally, say, from first principles. Now, imagine a particle moving on a straight line, okay, with a maximum speed of 2 units per second, right? 2 units per second. Initially, at the 2000th second, the particle is at -4 on the number lines. And then, what is the farthest point it would have reached at 2018th second? So, do you understand the problem now? Yeah. A particle is moving on a straight line. So, its maximum speed is 2 units per second. Let's say at the 2000 second, it is at -4. And then, what is the farthest point it would have moved, say, on the line at the 2018th second?
Yes, sir. This is a simple problem. The farthest point will be reached if the particle moves at its maximum speed.
Yeah, exactly.
So in the time interval 2000 to 2018 of 18 seconds, the particle at its maximum speed would have moved through 2 into 18, which is 36 units of distance. As it is given, f of 2000 is -4. So at time 2018, the farthest point will be reached by the particle is -4 plus 36, which is 32 units of distance.
Yeah, don't you see that the original problem is almost the same?
Exactly,
Yes,
sir.
exactly.
Actually here f dash x is the rate of change of function f, and here the answer of your question is to find the maximum value, nothing but f of 2018 equals to 32.
But this argument only says that the f of 2000 is less than or equal to 32. It doesn't say that the value 32 is actually reached.
Yeah.
So to show that, you need to exhibit a function which actually takes that value.
Okay, I think we can follow the Santi's line. So he told that the maximum distance will be reached when that particle moves at the maximum possible speed 2. So it is kind of, I have to find a function such that f dash x is equal to 2 throughout. So now it is a differential equation problem. So if f dash x equal to 2, so solving this differential equation we get fx should be 2x plus some constant. Okay. So now given that f of 2000 is -4. So that means f of means 2 into 2000 plus c should be -4. That means c should be -4004. So fx, the solution of this problem is fx equal 2x minus 4004, or we can write it as 2 into x minus 2000 minus 4. So this function will attain its value 32 at the point 2080.
Yeah, again, see, I am going to look at it as a schoolboy, an 8th or 9th standard school student. How does it solve this problem? See, look at, say, at the 2000, you start measuring the distance from -4. Is that right? If x is the distance covered, right, at the 2000th second, it is at -4. Is that right?
Yes.
So if you want at x units of time, x minus 2000, and then the speed is 2, so 2 times x minus 2000, but initially you are at -4,
Yes.
and therefore it is 2 times x minus 2000 minus 4.
Yes.
Given that f dash x is less than or equal to 2, and I think you have already observed earlier that it's fx minus 2x is a decreasing function.
Yeah.
Why don't you use that to get the maximum is 32?
Yeah, that also you can use.
Yeah. So, sir, with that observation, we can proceed as follows. So, f of 2000 minus 2 times 2000 is equals to minus 4 minus 4000, which is equals to minus 4004. Now we have that fx minus 2x is a decreasing function. Therefore, f of 2018.
So you are going to evaluate at 2018?
Yeah.
Yeah, okay, so.
And yeah, using so minus 2 into 2018, that will be less than or equals to f of 2000 minus 2 into 2000, which is equals to minus 4004. Therefore, f of 2018 is less than or equals to minus 4004 plus 2 into 2018, which is equals to 32.
Yes.
So this proves that if we have a function satisfying our given conditions, then it can take at the most value 32 at x equals to 2018.
You have already found a function also, right?
Yeah.
So essentially you solve the problem.
Yeah, so it's a nice problem, but again, I would suggest that you try the same problem with mean value theorem.
Again the same idea. We can use here mean value theorem as f of 2018 minus f of 2000 by 2018 minus 2000, which is equal to f dash c for some c belongs to open interval 2000 to 2018. But we have given that f of 2000 is equals to minus 4 and if f dash x is bounded above by 2 whole over the real number set. Therefore, we get f of 2018 less equals to 18 into 2 minus 4, which is equal to 32. f of 2018 less equals to 32.
So actually Kuntal suggested that this problem was solved by mean value theorem initially only. So maybe you guys didn't listen to that and we got different solutions now. 2 different solutions to solve the same problem.
3 different solutions actually.
So I think both of you got, in the quizzes you got very interesting problems, good problems.
Yes.
Do you have any more good problems in calculus?
Yes, so we had one on the properties of the Legendre polynomials.
Okay.
Is it about the zeros of Legendre polynomials in the interval minus 1 to 1?
No sir, actually we just had to compute some integral and use the orthogonality property of Legendre polynomial.
So may I interfere here?
Yeah.
In fact, Legendre, as you said, is a Frenchman. So you should pronounce him like Legendre. Well, but you are not wrong. Even in UK they say it Legendre. In USA they say Legendre. So you are free to choose.
Okay.
However, it's better to say Legendre. Please continue.
Okay.
No sir, we just had to use the orthogonality property of Legendre polynomial and we had to compute some simple integral. I am sure everybody here will be able to do that problem.
Yeah.
In that case, take this question and display it. I'll go with the Indian pronunciation, Legendre. So prove that the Legendre polynomial Pnx, nth derivative of x square minus 1 to the power n has n distinct roots, n distinct zeros in minus 1 to plus 1.
So one thing is clear and obvious to me, that if we take fx equals to x square minus 1 whole to the power n, then fx has zeros at 1 and minus 1 with multiplicity n. Hence, for 0 less k less n, the kth derivative of f will have a 0 at 1 and minus 1.
Yeah.
Redifferentiation reduces the degree of the polynomial by 1. And initially you start with x square minus 1 to the power n, so the degree is 2n, and you get the Legendre polynomial by differentiating it n times. So what is the degree of Legendre polynomial?
Yes, sir. The degree of Pnx is 2n minus n, which is n.
Correct. Let us look at the first derivative, namely d by dx of x square minus 1 to the power n.
Okay. So to compute this differentiation, then f dash x is equal to 2nx into x square minus 1 whole raised to n minus 1.
So yes, what about the zeros of this f prime x?
Okay, f dash x has degree 2 into n minus 1 plus 1, that is nothing but 2n minus 1, and also zeros of f dash x are 0, minus 1 and 1.
You say that this is a polynomial of degree 2n minus 1. So we expect that there should be 2n minus 1 zeros. But you have only given 3. 0, minus 1 and 1.
Yes, sir. We can see that plus minus 1 are two zeros of fx of degree of multiplicity n minus 1, and 0 is also a simple root. Taking multiplicities into account, we have 2 times n minus 1 plus 1, which is 2n minus 1. So the number of zeros is 2n minus 1, which matches with the degree of fx. And we also see that inside the open interval minus 1 comma 1, f dash x has a simple root.
Now similarly, look at the kth derivative fkx, that is same as dk by dx to the power k of x square minus 1 to the power 1 for n, k less than n. So what about the zeros of this kth derivative?
The kth derivative of f, that is dkf by dxk, has a factor x square minus 1 to the power n minus k. So the kth derivative of f has 1 and minus 1 are zeros, each of multiplicity n minus k. Therefore accounts for total 2 into n minus k zeros. We have to look for the other zeros. 2n minus k minus 2 into n minus k equal to k zeros. So now looking at the function f and its kth derivative, it suggests that the kth derivative of f has k zeros in the open interval minus 1 to 1.
Yes, you are on the right track. So please continue and search other roots of the function.
Yes, sir.
Maybe we can use induction to show that kth derivative of f has k distinct zeros in the open interval minus 1 to 1. So for k equal to 1, we can see that f dash x is equal to 2nx into x square minus 1 whole raised to n minus 1. And clearly 0 is the 0 of f dash x in the open interval minus 1 to 1. Induction hypothesis. Assume that kth derivative of f has k simple zeros in the open interval minus 1 to 1. Okay. To prove k plus 1th derivative of f has k plus 1 simple zeros in the open interval minus 1 to 1, assume x1 less than x2 less than x3 less than etc. less than xk are k simple zeros of kth derivative of f in the open interval -1 to 1. From here we can write -1 less than x1 less than x2 less than x3 less than etc. less than xk less than 1. Plus minus 1 are zeros of multiplicity n minus k.
You have now listed the zeros of the kth derivative, right? So you want to find zeros of k plus 1th derivative. So there are intervals -1, x1, there are n plus k plus 1 intervals you can see. So do you see any relation between zeros of a function and its derivative? Because k plus 1th derivative is the derivative of fk, right?
Yeah.
So can you relate this and then find the zeros? And then find all the zeros of fk plus 1.
We have Rolle's theorem, which states that if we have a function from closed AB to R, which is continuous on closed AB and differentiable in the open interval AB, such that it takes same value at the end points, then its derivative will have on 0 in the open interval AB.
Correct.
So here we have zeros of fk at xk, x1, x2 up to xk. Now we can apply Rolle's theorem on k plus 1 number of subintervals, namely -1 to x1, x1 to x2 up to xk minus 1 to xk and xk to 1. And we also have that kth derivative of f has zeros at -1, x1, x2 up to xk and at 1. So we will have k plus 1th derivative of f at 0 in the each k plus 1 subintervals, namely open -1 to x1, x1 to x2 up to xk minus 1 to xk and xk to 1. So which shows that if we have k plus 1, kth derivative of f has k number of 0 in open -1 to 1, then k plus 1th derivative of f has n plus 1, k plus 1 number of zeros in open -1, 1. So using principle of mathematical induction, we can say that nth derivative of f, which is nth degree Legendre polynomial, has n zeros in open -1 to 1.
Yes, good. Let us continue our discussion. In the last meeting of the Calculus Forum, you had shown us a movie exhibiting the power of these continuous functions, power of continuity. You had also discussed about a problem of cutting a rectangular cake with a rectangular ice topping of a different size by a straight line cut in such a way that exactly half the portion lies on the either side of the straight line.
Sir, shall I show them the picture? So that was my birthday cake, and the cake was like this. It was a rectangular cake, a pineapple cake with a rectangular icing, a chocolate icing. It was yummy, and this was how my cake looked. So the problem was to use a single knife cut to cut both the cake as well as the topping into two exact equal parts.
Since Professor Nair could not attend the last meeting of the forum due to some reason, I mentioned to him about the meeting and this problem. After hearing it, he immediately came up with one question. Professor Nair, could you mention that question here?
Yeah, cake, of course, both are rectangular. Maybe you may be able to do it in a slightly easier fashion. Suppose you have a pancake or dosha or something, okay, or cake of irregular shape. So suppose you want to cut it so that either the area equal on both sides or the volume equal on both sides, or let's say weight equal. One of them you can take into account. So can you place the knife in such a way that you get two equal pieces? So this could be slightly more general than these rectangular pieces on the top.
So we consider this to be the irregular shaped pancake.
Correct.
Yeah.
So actually I think we discussed this type of problem in our previous convex shape geometry, and for the sake of simplicity we took a garden of a circular garden, and it was filled with 1,000 tall trees. And our problem was like we have to find a straight line path through that garden, so that on the either side of that path there will be exactly 500 trees. So I think this problem is actually a general version of that problem what we discussed.
Yes, I think the solution procedure to this problem will be similar to the one that we used to solve it in the case of a convex geometry. So let me try to follow the same procedure and solve this problem. So let us consider a straight line cut OQP, something like this. This is O, Q and P, and let this be area A2 and this be area A1 and A2. So we see that area A1 is bigger than area A2. So now we fix the point O on PQ. Now when the straight line cut rotates through O, the area of A1 decreases and the area of A2 increases. So initially we had A1 minus A2 is greater than 0, and as we rotate we come to a second position, maybe this, let me name it Q1 and P1. So when it is in this position, we see that the area of A2 is much larger than the area of A1. So in this case we have A1 minus A2 is strictly less than 0. And it is also clear that A1 minus A2 is a continuous function of theta, the angle of rotation.
But Susmita, how do you measure angle of rotation theta?
So consider the polar coordinate system with O as the pole and a line through O as the initial line, such that the pancake lies completely on one side of the line. So something like this. So let us consider O here and let us consider this line.
And by intermediate value property,
Yeah.
since the continuous function a1 minus a2 is positive at some point and negative at some another point, so it must be 0 in between somewhere, and thus we get a straight line knife cut which bisects the region into two equal halves.
Yes.
Am I right, sir?
Yeah, right.
This only proves the existence. So can we construct such a line which will make make two equal parts of that irregular shape?
Yeah, so this is where, the theory and practice come into the picture. You may have a theorem which says there is a solution. Now you want to construct the solution. What do? Naturally, you have to use some numerical methods, right, in a certain mathematical problem. So here what you do is, instead of continuously moving the knife, perhaps you have to do discretely and see whether, the change in the direction, where the area A1 minus A2 changes. So you locate a place where some small strip will be there. On one knife it is negative, other strip it is positive. Then with that small strip again you cut into pieces. So you can get as good approximation as you want. But exactly finding is you have to do in an infinite process perhaps, which is impossible. So maybe here what the whole idea is, you fix a knife somewhere and rotating it. Okay, so it looks very artificial to me. Perhaps you to hold the knife, then let's say parallelly moving. So this is the kind of things happening in X-ray tomography and all. So instead of conical scanning, you may have a parallel scanning. So parallelly, suppose you cut it parallelly. So is it possible to get this? Suppose your knife is moving in a parallel fashion, not in a conical fashion. So is it possible?
I think this one will work, sir. So instead of taking continuous rotation, we can take another geometrical transformation, namely translation.
Yeah, that's good. Yeah, that's the thing. So you move slowly. The essence of the problem is that you move the knife in a continuous fashion, so that intermediate value theorem can be applied, so that existence can be asserted, right?
Yeah, something like this. If this is the pancake, then we can do translations like this.
Yes.
And maybe somewhere in the middle we'll have the exact knife cut.
you see that the solution is not unique. You have a solution in with a given slope, right? So just as in the case of this translation, you have infinitely many solutions. Even in your earlier rotation case also, by choosing different poles, we get different solutions. For example, if you take 2 points O1 and O2 as your poles, then the two solutions are different unless O1, O2 itself is a cut.
So what you are saying may be that the kind of shape you get one fellow gets maybe different if somebody else cuts.
Yes, yes. The two halves in geometric shape may look different.
Yeah, so this dosa actually prepared by me because I am not an expert, but I know how to survive. So it's a irregular shape, not like a usual the way ladies generally prepare or whomever the experts prepare, I should say. So now I am putting a knife here, the first method. So if you have here knife, you have A1 minus A2 is a very large number. Okay, so slowly A1 minus A2 becoming smaller and smaller. Then finally again smaller and smaller. This is again positive. Oh, now it is again negative, negative, etc. So you have to go slowly from here to here. Then it becomes 0. The point becomes 0. It's like this. You have the cut. Only thing is that we don't know exactly the point. This only existence only proved, right? So the construction is that when you have positive here, negative here, then again I have to come back, again negative, again positive, negative, positive, negative, positive, finally I get slowly 0. So I get the cut here. So this is the so-called polar, using the polar coordinate, moving, holding the knife one place and then moving. Okay. Now let us look at this, not this way. I am just standing here, just scanning it in a parallel way. So again here, A1 minus A2 is 0, A1 minus A2 is slightly positive, 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 finally positive, positive. It crosses 0, then negative, crosses 0 here, somewhere here. So I get again, got it. So I have almost my piece is almost slightly less than the piece which Kundal got it.
But the same problem in higher dimension will be much more difficult, and the intermediate value theorem does not work there. So we'll need the more sophisticated techniques from algebraic topology.
Well, this cutting the cake is very nice. So I would like to present you with something else. Say, I have a samosa here, and then we want to cut it into half, so that both of you will be satisfied. Can we do that?
It looks impossible to me.
Actually what you want is not only including the fillings should be exactly half. Now, it looks very difficult, but you have two good theorems in algebraic topology, Ham-Sandwich theorem and Borsa-Coulomb theorem, which answer this question partially. Of course, but it involves a lot of algebraic topology results. You can Google and find out the proofs yourself, or if anyone wants, I can send references.
So Smita, I think before winding up this session, I would like to pose another problem.
Sure, sir.
So this also involves some calculus.
Okay.
So in fact, this morning when I was coming to the office by bicycle, I saw there are many speed breakers of various types. With some of the speed breakers I could see I could come easily, whereas some of them are very hard. In fact, my back gets jerk. So then I found that some of them are a small circular arc, circular arc of small radius. Some of them are of circular arc of large radius.
Is it something like this? Some are like this and
So
some small.
yes. So when you go that point where you change, if it is the small radius, then what happens is that I have a lot of problem, because there is a sudden some problem happens when the cycle moves. So what is it? How is it connected with the calculus?
You can see that one thing, and at the point A where the speed breaker starts, and at the point B where the speed breakers end, Okay, in between there is no discontinuity of the path, right? But on the path there are some corners, and at these corners, I mean, the motion changes abruptly. The direction of the motion changes abruptly.
So what? Abruptly means what in terms of mathematics?
I mean,
Direction of what changes?
direction of the motion of the path changes.
Yeah, so
abruptly.
you can think of the cycle path as a curve,
Yes.
right? Smooth curve, not smooth curve. Then some point, if you look at the slope, at some point the slope changes, right? That is 0 to some strictly positive number, then remains maybe continuously sometimes. Then again there is a sudden change.
Yes, yes.
So the change, at that point, even the curve is not even differentiable. The function is not even differentiable, and the left and right derivative, there is a jump, correct? So that is the thing which causes, and also it's change in derivative also. That is second derivative. So that also matters here.
So what if the bobs are trapezoidal in shape?
Now I understand, sir. On the speed breaker, the rate of change of the tangent line plays important role here.
Yeah, that's true. See, for example, now the circle, right? If it is semicircle, what happens? Suddenly there is a infinite slope is infinite, right?
Yes.
Is it not? So if it is part, not semicircle, part, etc., it becomes smoother, again smoother. So it matters a lot. Where the crossing, what part of the circle is taken into account. Correct?
Yeah.
So the derivative, how it changes and how much changes, this all plays a very important role. You are right.
See, Mansoor, in the first case, curve is almost straight line and curvature is very small. And also tangents do not change so much. This enables the cyclist to cross the road very easily. Whereas, as the radius decreases, the curvature increases. And the change in the direction at the point A and B much more faster than the previous one. So that is why in the second case, this becomes more difficult for the cyclist to cross the road.
Yeah.
Well, that's good. If instead of the circular arcs you have the trapezoidal ones,
Something like this.
yes.
It will be really funny to have such speed breakers on the road.
Well, you have
Yeah,
those
there
things
are,
in
there
IIT.
are. In front of ICSR building, it is like that.
Yes.
There at least, not infinity. Here it's infinity, right? Curve itself is discontinuous as a function of the, the down, right?
So in this case, it is almost impossible unless we lift the bicycle.
Yeah.
Yes,
So
exactly.
we have to really think about.
Well, you make the height smaller.
So maybe while constructing the speed breaker, I think they have to consult calculus experts like us, right? So maybe we should think more about this. What kind of speed breaker has to put, and what part of the circle you have to put, or it need not be circle. It can be ellipse or any what kind of curve, what place it has to be cut. All these things is nice to think about it.
Yeah. So I guess it's time for dinner now. Let's wind up this session, and I like to thank you all for actively participating in this. Hope it was really useful to each and everyone. Thank you to all the professors.
Thank you.